So, what does it look like when we charge a capacitor? We've talked about charge being on these plates, positive Q and negative Q, but where is that charge actually coming from? Well, we need a voltage source. Somehow that charge is getting there. And so we've talked about how we can create a potential difference due to separating charges either mechanically or chemically through a battery. Mechanical systems are pretty complicated to talk about, so we're going to focus on using batteries. So we've said that our battery has this EMF, which creates a voltage difference from the positive to negative terminal. Now, something then happens called a current, and this is important, and we defined current at one point earlier in the class, but we are now coming back to it. Current is the flow of charge. We are taking some of our positive charges that are at our positive terminal, and we are thinking about them marching on and ending up on our capacitor. Now you might say, Dr. Ackerman, I know positive charges don't move. It's actually electrons that move. Don't worry about that. That's going to confuse you, but we'll talk about that in like another video or two. So right now, just think about positive charges moving. So we then end up with positive charges coming from the battery onto our positive plate. However, we know that for a capacitor, we must actually have the same number of excess positive and excess negative charges. So we need negative charges on this other plate. Well, where are those going to come from? Again, we're thinking about the motion of positive charges. Yes, that's a lie, but go with me right now. So if we keep marching positive charges over here, well, that leaves behind excess negative charges. So what that looks like is if I have 3 positive charges march this way, I have 3 positive charges march off that bottom plate, and we end up with equal charge on each plate, but excess charge. Now, this process, which we call charging, is when the potential difference across the capacitor is less than the potential difference across the battery. Now, this is hugely important because note what's happening right now. We are actually talking about charges moving. Remember that previously we said that whenever you have conductors, and remember that wires are conductors, that whenever you had conductors before, we said that charges weren't moving, but now they are. We say that we're moving charges from the battery to the plate. So why is this okay? Previously, we were talking about conductors in electrostatic equilibrium. This situation here is not electrostatic equilibrium due to this condition. We don't have equilibrium. We have one part of our system that has a different potential than another. That means that charges are going to move, which creates current. So this is really important, which is why I'm going to keep stressing it, is that up till now we were dealing with electrostatics. Charges were not moving. Now charges are moving because we've introduced a source of potential. And right now we're talking about charges moving onto capacitors, but for the next couple of weeks we're going to be talking about charges moving. So we've really hit a breaking point in the class. So again, this charging process is fundamentally when the voltage across the capacitor, or the difference in electric potential between the two plates, is less than the battery. But we said we're going to keep shoving charge on here. And you know that the charge relates to the potential difference. So eventually, these two charges become equal. The potential difference becomes equal. And we then say that our capacitor is charged. Once these are equal, now we are actually back to electrostatic equilibrium. And what does that mean? Well, if we are back in electrostatic equilibrium, we do not have any charges moving. I'm failing at spelling. Right? We have no current. And that's really important. So basically, we charge based on the battery for a little bit, and then it stops. This is a really fast process. If we're talking about ideal wires, and in a couple of videos we'll talk about what is and is not an ideal wire, but if this is an ideal wire and an ideal battery and an ideal capacitor, this process is actually instantaneous. But we have to think about the things that make this system non-ideal to actually understand why it takes a little bit of time. But this process, even in a standard situation with like a real-world wire, depending on the capacitor and the battery, we might be talking about nanoseconds or picoseconds. These are really fast processes. So it's really important that you understand, again, this distinction here, that here it's charged, we have electrostatic equilibrium, we have no current, and our two potentials are the same. In the previous scenario where it's charging, we have a greater potential from the battery than the plates, so we have current flowing, which means charge is actually moving from the battery to the plates. So two big differences. In this case, we do not have electrostatic equilibrium. Charges can move. In the charged case, we do have we do not have, I'm messing this up. Charging, no electrostatic equilibrium, charges move. Charged, I can't put the accent on that last syllable, your charges are not moving anymore, you are in electrostatic equilibrium. So a lot of different things to keep track of here, but make sure that everything seems logically consistent to you, and that will help indicate that you have a good understanding of the scenario. So there's one last thing that I want to talk about, and this has to do with a certain type of conceptual problem that I really like. And so I assign this all of the time, and I want you to help talk you through how to think about these. So basically, you're going to be given some sort of initial system. You might be told what your potential is of your battery. You might be told what your capacitance is. You might be told something about the electric field, the area of the capacitor, or the spacing of the plates. We frequently use parallel plate capacitors for this problem, but you don't have to. Then some sort of change is made, typically to one of these variables. And then you're asked to predict what's going to happen to a different variable. Now, obviously, one can't force electric field to change and say, well, how does that change area? So some of these are more likely to be in the situation that's changing, and some of these are more about the prediction. So what I'd like to focus on here is how you actually think about all of these different variables and changes that can occur. So for instance, let's say I've taken my capacitor and I've said that I am changing the spacing between the plates. I am squeezing my capacitor, for instance. Well, if the battery is still attached, you have kept the voltage difference between the plates fixed, right? As long as a battery is attached to the capacitor, that voltage difference is fixed. Now, if the battery has been removed, you start at some delta V, but now delta V might change as you make adjustments to your capacitor. But if the battery is still attached, delta V is fixed. Now, if we've removed the battery such that our electrodes are isolated, no charge can flow, well, the Q on each plate does not change because there's nowhere that it can go to. And so, again, the big question is your battery attached or not? And in that case, you either think about your voltage difference staying the same or your charge staying the same. Another thing to think about is that if I'm telling you that the area of the plates can change, and that has to do with there are certain types of capacitors called variable capacitors, we actually change the overlap between the plates. So that's one way A can change. Or D can change by, you can imagine pulling the plates apart or squeezing them together. And if that happens, C, your capacitance is changing. And depending on what's happening with the battery, either V or Q must also be changing. The last thing to think about is that if you're asked anything about electric field, don't assume that that stays the same. Make sure that you're always relating electric field to the potential difference across the plates and the distance between them. So that's just a little bit about what to think about for these types of problems. Again, I think they're really interesting to think about, and it's one way to let you connect all of these different variables together.